This video will focus on the pH system, both as a concept and how to do the math behind it. Okay, and then also we'll look a little bit at indicators and how those help you determine pH. So when we're talking about the pH scale, what are we actually talking about? pH stands for percent of hydrogen. So what it's actually measuring is that amount of hydrogen in your solution. So it's a way to express your strength of the acid and base. Okay, how much acid and base are actually dissociated into the solution. Okay. The concentration numbers that we've been looking at in relation to how much is there were like 10 to the negative 1, 10 to the negative 7, 10 to the negative 11. And what the percent hydrogen calculation allowed us to do was to get rid of those very large negative exponents and bring them into integers instead. Okay? It was just a way to not always have that really large negative number. It's kind of a funny thing to do, but it's just an easier way to look at it in many people's opinion. So you probably already know that we're looking at the pH scale. 7 is water. Below 7 is acid, meaning you have a very large percent of hydrogen in solution. And when you're above 7, you're in your basic range, because if you don't have a large percent of H+, then you have a large percent of OH- in solution. On the right, there's a list of different things with different pHs, so you can see kind of the range of things we're talking about. Battery acid and gastric acid have a very low pH, which means they have a lot of H+ in solution. Even Coke or juice, those are all acidic and have a decent pH in relation to how much H+ they have in solution. And then if we go the other way, above 7, there's a list of different things that are basic. Soap, cleaners, things like that. That would actually be basic in solution. So what is the relationship between the concentration of H+ and the percent hydrogen pH calculation? The relationship is that the negative log of the concentration of H+ will give you the pH of the solution. Okay? It's simple as that. The most common mathematical mistake made for this calculation is to forget the negative sign in front of your log. Okay, that negative sign gets rid of the negative on the exponent so that your pH is always positive. Okay, your pH will always be positive, and it's in a range of about 0 to 14. So pH equals a negative log of the concentration of H+. Those brackets mean concentration or molarity. So here's 2 example problems that we'll do that are fairly simple in terms of using pH. Log is base 10. So taking the log of something that's base 10 simply means in the end we're going to be reporting our exponent. Now, since it's a negative log, this negative from the exponent goes away, and the pH for this concentration of H+ is 10. If you have a number in front of your 10 to the, that ruins your ability to simply take this exponent down and report it. Now you're actually going to have to calculate the negative log of this then, and what you get for this calculation, you get 4.7 for that guy. So you can see how your final answer is very close to what this exponent is, -5, but the magnitude of how far it is off of the -5 depends on how big this number is. Okay, the bigger it gets, the closer this would get to then 4, as this number actually becomes closer to 4. So that's a little way to actually check your math and make sure you're doing it right. So how do we solve for concentration then? If you have a pH meter, for example, and you determine that the pH of Coke is 3.12, how do we figure out what the concentration of H+ is in the solution? Well, we have the relationship pH equals the negative log of the concentration of H+, but a lot of people have a hard time getting rid of that log. Okay, so we walk through the math here on this screen. If you take the negative and move it to the other side, then negative pH equals log of the hydrogen concentration. And then you take the anti-log, the 10 to the of both sides. And what that's going to do is get rid of the log, right? It'll take 10 to the negative pH. And if you raise log to a power of 10, the log goes away, and all we have left is the concentration. So to solve for concentration, when given pH, you go 10 to the negative pH, and that'll get you concentration of H+. For this problem, if you go 10 to the negative 3.12, you'll get the concentration of H plus to be 7.6 times 10 to the negative 4. Okay? So really there's two equations potentially to remember for pH. pH is the negative log of the concentration of H plus, and then also 10 to the negative pH, is the concentration of H plus. So it depends on what you're solving for. Now, so far all we've been talking about really is H plus. You can get concentration of H plus to pH or pH to concentration of H plus. But we have a second half of our acids and bases always, which are the base, the hydroxide. Okay? And since acids and bases are opposite, we actually have something that we can use called POH. And POH and pH are opposites. Now, POH is simply a convention that we use to calculate things. POH is not measured. We don't have POH meters. We don't have any way to determine POH. It's just a helpful convention that we use to get from H plus to OH minus to determine the basic nature of the solution that we're working with. Okay? And the two equations that we've got, pH is the negative log of H plus, and 10 to the negative pH is concentration of H plus. We can do the exact same things with POH. Okay, so POH can equal the negative log, but that POH has a relationship with OH rather than H plus. And because of how 10 to the negative 14 for your KW will exist in equilibrium between H and OH, pH plus POH has to always equal 14. Okay, that 10 to the negative 14 for KW is driving our relationship between pH and POH. So if you know POH, you know pH simply by subtracting. And from that, you can get information about both your base and your acid in any solution. The difficulty for these problems simply becomes keeping an eye on what you're measuring, hydroxide or hydronium, H plus. Okay. Because if you stick a concentration into your equation, the negative log of concentration equals your percent something. If you don't know what that percent something is, then you can get the problems wrong. Okay, so it's the only small thing you have to keep an eye on, and we'll do some example problems here in a sec. So here is really all your equations so far just dealing with pH. Okay, we have a KW relationship that relates H and OH. And then we have a pH-POH relationship that relates H and OH. Keep an eye on those two equations, KW and that pH-POH. Those are your two equations that relate H plus and OH. They're going to allow you to convert from one to the other in order to solve problems. Okay? And then we've got pH is the negative log, POH is the negative log, and then 10 to the and 10 to the. So if you see, these equations are very redundant. Okay, I'm able to list 6 different equations and 1 KW number, but really it's like 3. Okay, we really have 3 relationships, 3 main relationships, and then the pH plus POH equals 14 relationship. So let's look at how all of these things are applied. Here's our first problem. A solution has a pH of 1.86. The question is, what is the hydroxide concentration? I said the number one thing people get confused is they don't know what they're solving for. Okay, I see that I have pH, and right away for me, I know I have 2 potential equations. Okay, just generally, the negative log of some concentration is going to get me P something, and 10 to the negative P something is going to get me concentration of something. So I look at this, I'm like, oh, I have a P. So if I go 10 to the negative 1.86, I'm going to get concentration of something. You got to make sure you know what that concentration is, though, because if I look at this problem, I see that I'm solving for concentration. So I could think, boom, I'm done with this problem. But you're not, because you right here, this is for H plus, which means this is for H plus. And if you look at the problem, you're trying to solve for hydroxide, which is OH minus. This concentration is not what you're looking for this particular problem. So now I have a choice. There's 2 ways to relate H to OH. One is through the pH-POH relationship, and one is through KW. Okay. Given the fact that I'm given pH, the easiest way for me personally to solve this problem is to calculate pOH and then go 10 to the negative pOH to get concentration of OH. So 14 minus 1.86 is going to get you your pOH of 12.14. And then if I go 10 to the negative 12.14, that is going to be my concentration of OH minus, since this right here is my pOH. So I cut 10 to the negative 12.14, I get a final concentration of 7.24 times 10 to the negative 13 molar. So you can see how it's really important, again, to keep track of whether you're solving for H or OH, because they relate. But if you had just gotten 10 to the negative 1.86, your final answer would have been concentration of H+, which would have been wrong. So let's talk about how pH is measured. There are lots of ways to measure pH. We have pH paper, we have pH meters, we have the litmus paper you guys have already used before. Okay. The one thing you haven't used much of is something called an indicator. And what indicators are just dyes that when you put them in solution, they actually change color based on the pH. Okay. The indicator only works in a specific range of pH, which means if the indicator is orange, it's specifically saying the range of pH is relatable to the color that you're observing. Okay. And there's actually natural indicators. In some schools, when you're little, you may make red cabbage leaves indicators. So have you ever done that, boiled cabbage leaves to get like a purple indicator? I mentioned in some classes how blueberry juice is an indicator. My husband now takes blueberry juice left over from after the kids eat blueberries, and if you make it acidic, it turns like a darker black blue, where if you make it basic, it's like bright red pink. And he goes back and forth and shows my kids the change in color, which is kind of fun. So an indicator is just another way to measure what the pH is. Okay. We have something called a universal indicator, which is what's shown in the picture on the screen here. There's a lot of other indicators though, and the biggest thing about other indicators is some indicators don't show a color at every pH. Some just flip colors at a certain pH. And that's what this says. Okay? Some are not like universal indicator, which are different color at every pH. Some change color at a specific pH. When indicators change color at a particular pH, what that allows you to do is know when you're at that level of percent hydrogen or percent hydroxide. I'm going to talk more about pH when I'm with you actually, so I can show these to you. But the biggest thing here is to look at the fact that litmus paper actually shows you when you're acidic and when you're basic. Phenolphthalein is pretty close to the change from neutral to phenolphthalein is really close to the flip for when it goes from acid to base. So we use that a lot of times to show whether you're an acid and whether you're base. The rest of the indicators on the screen don't change colors when it's acidic or when it's basic. They change colors at specific pHs, and there's a reason we would use them. But again, I want to do this in person with you guys because it's a little confusing. pH meters are the best way to test pH in terms of they're the most precise. You can get your best measurement for pH. We don't always use them because honestly, they're not as easy to use as you would expect. Okay. Number one, they have to always be calibrated based on what 7 is. They're looking for conductivity, amount of dissociation in solution, and since hydroxide and hydronium are both in there, it makes a big difference that you calibrate them each time correctly. The other thing about pH meters is frequently we don't need as much precision as they give us. Okay, most of the time we're simply looking at how far we are on our scale in relation to like, are we at 2 or are we at 6 for our pH? We don't care if we're at like 2.2 or 6.7. That doesn't matter as much. So the precision kind of is not needed a lot of times with measurement. Okay. These problems, I believe, are not hard. I only showed you one example. Okay. Have your equations. Just remember what you're focused on is H versus OH, in terms of what you use. Okay, if you have a concentration, negative log of concentration will get you P something. If you have P, 10 to the negative P will get you the concentration of something. That's all it is. So go ahead and try the worksheet and then do the form and have a nice night.